So today we will start a new book. The name of the book is Calculus and Analytic Geometry. The authors are George B. Thomas and Ross Alfini, and it's a ninth edition. Okay, and we will start with the chapter number 8. Title is Infinite Series. Right. So before going to the infinite series, let's see some terms that are helpful in dealing with the series, right? So first is sequence. So what's a sequence? So it's a function whose domain is the set of natural numbers. So this is important. So its domain is a set of natural number to any set. S here is here. S can be R, C, right? Complex number, or Z, like anything, etc. So it can be any set S, right? So when you call this function a sequence, when you arrange the images of the sequence in the order of natural numbers. So when you arrange the images in this order, you call this as a sequence, right? And the notation that we use in this book is an. So now the sequence an will be equals to like a1, a2, a3, a4, and up to so on. So these are the terms of the sequence. So every subscripts represent the corresponding term. So if 1 represents the first term of the sequence, 2 represent the second term of the sequence, 3 represent the third term of the sequence, right? And so on. So nth term of the sequence will be an, right? So this will be the nth term of the sequence, right? Then we have here next term is convergence of the sequence. So let's understand the meaning of convergence first. So as the this term implies convergence, that means your sequence will go to some point, some fixed point, so, say L, right? So when do you say that your sequence is going to that particular point? So we use the definition is the sequence. Let's see by definition first. The sequence an converges to a number, say L, if every epsilon, okay, that is a positive number, there exists a positive number, or you can say there exists an integer n such that an minus L is less than epsilon for n is greater than capital N. That means whenever your small n, so small is belongs to natural number, right? So whenever this n is greater than this capital N, this inequality will hold, right? That means the difference between the terms of the sequence and that point L will be less than this capital L, right? So whenever and you put n is greater than capital N, then this inequality holds. That means the term of the sequence and that point L, the difference between those two will be less than epsilon. Here epsilon is every positive number, any positive number, okay? So if it's true for every epsilon, then you will say your sequence is tending to that point L. So one of the way to use the definition is that you must draw, because to use this definition you must know this L, right? You must have an idea that where your sequence is tending to, okay? After that you can use this definition. So how you will get that idea? So first is to draw the term of the sequence. So suppose you have a sequence an equals to 1 by n. So now term of the sequence will be a1 to n equals to 1, so you will have 1, right? A2 will be 1 by 2, A3 will be 1 by 3, 1 by 4, 1 by 5, 1 by 6, and so on, right? So you have to draw it on a real line. So here is 0, here you have 1 and 2. So first term is A1, right? Second term is half, that means A2. Third term is 1 by 3, that means A3. Then fourth term A4, then A5, then A6, then A7. So we see that our sequence is tending to point 0, and we know that your n belongs to a natural number, okay? That means and your sequence is this, that means it will always be greater than 0, right? So it will never get to 0, but it is tending towards 0, right? So when you put n is infinitely very large, then that means you will tend very close to 0. That means your L is 0, right? So now you will use the definition. That means an minus L will be less than epsilon, okay, for all n greater than capital N. So your purpose is to find this capital N. So just put the values and let's see for what value of n you this inequality will hold. Okay, so just reverse it. So that means for this one, so your capital N is here 1 upon epsilon, right, plus 1. You can write it like this one, or you can just take the greatest integer of this, right? So that means greatest integer, or you can say ceil function, you can like this one. Okay, so that means whenever your n is greater than 1 upon epsilon, this inequality will hold. Now you can check it. Suppose your epsilon is 0.5, that means 1 by 2. So that we will see that for what value of n. So that means an minus 0 will less than 1 by 2, right? So that means 1 upon n is less than 1 by 2. That means n is greater than 2. So as your n is natural number and is greater than 2, that means you will start putting n from 3, right? Because the next natural number comes after 2 is because you can't put 2. So the next natural number that you will put is 3, right? So whenever you put n greater than 3, so let's see. So we'll start putting n 3, 4, 5, 6 and so on. So for 3 you will have 1 by 3, okay, so less than 1 by 2, right? So it is true. So again 1 by 4 is less than 1 by 2, 1 by 5 is less than 1 by 2, and so on. You can go like this, right? So that means an minus 0 is less than epsilon. Here epsilon is 1 by 2 for all n greater than equals to 3. So for this epsilon, okay, you have n equals to 3. So suppose you get this, you have this epsilon, okay, for this you will get some another n. Okay, the way you find this n is remain the same as we have done earlier, right? So again, epsilon can be anything. It could be this. So for this you will have a different value of n. So your purpose is to find this n, okay, and to use this definition you must know this L first. You must have an idea that where your sequence is tending to. If you don't have this idea, then you can't use the definition, right? So I told you the way that how you can have idea about the value of this L. That means to what value or guess to what number your sequence is tending to, right? So this is done up to here. So if you have any doubt, you can ask.